places in the universe where reality behaves strangely. And then there are black holes. They do not glow, they do not shine, they do not reflect, they erase. Somewhere in the quiet darkness between stars, a region of space exists where gravity does not simply pull, it dominates. A place where escape is not difficult, but impossible. Where time does not flow as it should. Where cause and effect begin to distort. Nothing about a black hole is normal. Not its birth, not its structure, not even its shadow. And yet these objects are not rare accidents. They are woven into the architecture of the cosmos itself. At the center of our own galaxy lies one, a gravitational anchor millions of times heavier than the sun. But before we can understand why black holes are so deeply unsettling, we must begin with something familiar: a star. Stars live long, predictable lives. They are enormous spheres of plasma held in balance by a delicate tension. Gravity pulls inward. Nuclear fusion pushes outward. For millions or billions of years, this equilibrium holds. In stars like our Sun, this balance ends quietly. The outer layers drift away, leaving behind a dense white dwarf, a stellar ember slowly fading. But for the most massive stars, the story turns violent. When a star at least 20 times the mass of the Sun exhausts its nuclear fuel, fusion stops. The outward pressure vanishes. Gravity, unopposed, takes control. The collapse begins instantly. Despite their name, black holes are not invisible because they are empty. They are invisible because they trap light. But the region around them can be violently bright. As gas and dust spiral inward, they form an accretion disk, a rotating ring heated to millions of degrees. Friction and magnetic turbulence generate intense X-rays and gamma radiation. Some black holes launch relativistic jets, beams of charged particles accelerated to nearly the speed of light, extending thousands of light years into space. These jets are powered by rotational energy. The black hole itself can spin, dragging space-time around with it in a phenomenon known as frame dragging. Even emptiness near a black hole is not stable. Magnetic fields twist, plasma arcs, radiation flares. The darkness hides machinery of terrifying efficiency. Then comes the deeper problem. If something falls into a black hole, its mass, its charge, its angular momentum remain measurable. But all other information about it appears lost. Quantum mechanics, however, insists that information cannot be destroyed. Yet, black holes seem to erase it completely. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Through quantum effects near the horizon, they emit faint radiation, now known as Hawking radiation. Over immense spans of time, a black hole can evaporate. If it disappears entirely, what happens to the information it consumed? Is it destroyed, encoded in subtle correlations, or stored on the horizon's surface? One leading theory suggests the event horizon behaves like a holographic boundary, preserving information in 2 dimensions. If true, the universe itself may be holographic in nature. Black holes are forcing physicists to reconsider the fundamental structure of reality, not because they are exotic, but because they expose inconsistencies at the heart of our best theories. And this is only the beginning, because there are black holes that spin so fast they drag space-time into vortices, black holes that may collide, shaking the fabric of the universe itself, black holes that could outlive stars, galaxies, even the era of light.
If black holes are not normal, it is not simply because they are extreme. It is because they reveal that normality itself is fragile. And what lies beyond the horizon may not be the strangest part at all.